Thank you. And thank you for the very kind invitation to be part of this conversation. I'm Ashwin Seshadri from these two centers in ISC. I'm going to talk about a couple of problems mainly where I think some very, very simple models have seemingly given us some insight. I'm hoping this will be more in the nature of a conversation, so please do interrupt me at any time. I'm thinking of pausing after I talk about the first problem, and then we can have a discussion there and then go on to the second. So here's a diagram from a paper that came out a little over a decade ago. It shows global warming versus cumulative emissions. Each color is a different climate model, or rather a different Earth system model of intermediate complexity. Each point is a different emission scenario. And basically, this figure shows that global warming is roughly proportional to cumulative emissions. And together with some other studies that came out around this time, these studies taught us in the community that you can think of global warming in these more complicated Earth system models, and also observations. I have a slide right at the back. We can go to the observation slide if you ask for it. But we
Ashwin, a quick question for you. You're starting this model from 1750 in the x-axis to 2500.
Yeah, so these are, so what happens here? How do you get the x-axis? You take a cumulative emissions curve, you feed it into this EMIC Earth system model of intermediate complexity. You take the area under the curve, and the assumption is 1750 is a good reference point for the time of the time in the Industrial Revolution when the emissions started.
So even the time that we know from 1750 to now, these models don't agree.
Where?
Even this last 250 years, these models are not fitting to the data.
What do these models show? These models show that in any given model, global warming is roughly proportional to the area under the emissions curve. Across models, the slope of that relationship is different. Okay, so in any given model, pick a color corresponding to a model, and the only difference between all the different points is the model is the same, the emission scenario is different, and these are all emission scenarios where the emission goes up, comes down to practically zero. So how do you find maximum emissions on the maximum warming on the y-axis? Well, it's some linear function of the area under the emissions curve. So this is a feature of the more complicated Earth system models, which have the relevant carbon cycle feedbacks that give rise to this proportionality. But the proportionality is between cumulative emissions, that's the total emissions on total area under the emissions curve, emissions versus time, and some measure of global warming. Right? And together, this and other studies that came out around the same time, yes. That's right. Yeah, that's like some measure of multi-model uncertainty. That cloud shows the uncertainty across the ensemble of models. Sorry? Yes. Each point is a model and a combination of a model and a scenario. So each color is a different model. Each point is a scenario for that model. What's the difference between the scenarios? They all have different emissions trajectories, and therefore different areas under the curve. And therefore, if you were to plot global warming versus time, what's the maximum value? Right? That's on the y-axis. And together, these studies have taught us that global warming is roughly proportional to cumulative emissions. I'm just highlighting one of these studies here. And this, of course, has been discussed and taken up by the IPCC. So here's a quote from the report that succeeded this body of work that came out, I think, around 2009. The ratio of global mean surface temperature change to total cumulative carbon emissions is relatively constant and independent of the scenario, but is model dependent as it is a function of cumulative airborne fraction of carbon in the transient climate response. For any given temperature target, higher emissions in earlier decades therefore imply lower emissions by about the same amount later on. So there's a lot going on in this paragraph, but there are really 3 points. The first is the proportionality that we saw earlier, right? So the ratio between the surface temperature change to the area under the emissions curve is relatively constant for a given model. Model uncertainty, the question of model uncertainty, it's model dependent, depending as it does on other things in addition to the cumulative carbon, which is the airborne fraction. So differences in the airborne fraction of cumulative carbon dioxide across models, and the statement about the implications for carbon budgets, right? That's the last one. So for any given temperature target in a given model, you can work backwards and find out the cumulative emissions budget. And this implies that higher emissions early on to stay within that cumulative budget requires lesser emissions. later on. And this is a very succinct statement, but all I want to say here is that cumulative emissions accounting, i.e. the last statement, does not require proportionality between global warming and cumulative emissions. It only requires path independence. We'll define that in the next slide, between global warming and cumulative emissions. In other words, global warming should be a function of cumulative emissions alone, but that function doesn't necessarily have to be a linear function. So here's what we mean by path independence in a much simpler model, an energy balance. These are not Earth system models of intermediate complexity. Here we're feeding, yes.
Please excuse me.
Please.
But if I can just take you back to the last slide.
Yes.
It makes a difference between scenarios and models. It says is relatively constant and independent of the scenario, but is model dependent. And can you just pass that? So
parse that, yes.
Yes,
yeah. So what's the first part? Ratio of global mean surface temperature change to the cumulative anthropogenic carbon emissions is relatively, the ratio is constant and independent of the scenario, but is model dependent, right? So what does it mean? To a good approximation, I can treat all the scatter for a given color as a straight line. So to a good approximation for a given model, if I seek to find out global warming from anthropogenic CO2, I simply integrate the area under the curve. But it's proportional for the more complicated Earth system models. Yeah. But it's model dependent because, of course, the slope is a function of model. And so here's a case where there's what we call path independence between global warming and cumulative emissions. Global warming is a function of cumulative emissions alone for a simpler model. But of course, nobody will look at this and say it's a straight line. Right? And this is a much simpler energy balance model that doesn't have the kinds of feedbacks that the emics have, which give rise to this proportionality. But they do have path independence, and path independence is a more general phenomenon that occurs from the most complex models to the simplest energy balance models with 2 time scales. And so this is one such model. You basically feed in these emission curves through this model, and then out comes this path-independent relationship between global warming and cumulative CO2 emissions. Now, this is a 2-box energy balance model. It has 2 time scales. There's a fast time scale, tau f. There's a slow time scale, tau s. It's interesting about the global warming problem on decadal time scales, vis-a-vis our interest in how the rest of the century is going to play out. Those timescales of interest are intermediate between the fast time constant and the slow time constant. And so then you can approximate the response in these models as being you can approximate the fast response is being in equilibrium with forcing. And that's what we've done here. So the familiar weighted integral is missing in this case, and that's because we've assumed that the fast response is in equilibrium with forcing. We also have another parameter, tau d, which is important to our overall story, but it's a part of the story which I'm not going to cover in today's talk. But it turns out that for this problem, this is more important. It's a coefficient. It's related inversely to the coefficient of the slow response, and turns out to be more important for our problem than the slow time constant itself. Now, another reason for making this equation explicit is we can see then what global warming T of t depends on. Time makes an explicit appearance. That's because of the inertia in the system. There's an integral, and so there's a slow response. But also it depends on f of t. F of t is what's called radiative forcing. You've encountered this in a bunch of lectures in the last couple of days. And radiative forcing, for our purposes, all we need to understand is it depends on the excess CO2 in the atmosphere. It doesn't depend. So there's a precise form of radiative forcing for CO2, but for our story, it doesn't. The point is, it doesn't matter what that form is. All that matters is we need to understand in turn how to decompose radiative forcing. And we know that radiative forcing depends on the excess concentrations in the atmosphere. And so, yes. Slow is deeper ocean. Fast time scale is atmosphere, cryosphere, land, and the mixed layer, ocean mixed layer. Right? And so fast time scale is bounded from above by about 10 years. It's less than a decade across models. If you were to try and fit these models to the more complicated Earth system models, you would conclude that the fast time constant is well less than 10 years. And so it's, and if you're interested in how this T of t evolves over a time scale of several decades, you can assume that the fast response is therefore in equilibrium. But the forcing is a function of excess concentrations. Excess concentrations one can write as cumulative emissions times the airborne fraction of cumulative emissions. This is the same airborne fraction that is being referred to here. And so here's the problem for us, right? Under what conditions can we know that this is a function of 3 arguments, T, cumulative emissions, and the airborne fraction. So under what conditions can I approximate, and this is already an approximation, but it's a good enough approximation, but under what conditions can I further approximate this function as a function of cumulative emissions alone? And that's, right, under those conditions, I'd have path independence. And so now we look for those conditions. And here's a schematic view. I should also say that...
Excuse me?
Yes.
Is there a reason why this separates into 2 distinct timescales, a fast and a slow one?
It's just a 2-dimensional system of ordinary. It's two coupled ODEs.
Okay.
Right. So when you integrate a system of 2 linear ODEs or linearize,
right, and that
you can write the system in terms of time scales which are inverse eigenvalues. So the 2 eigenvalues of the Jacobian will give you the fast and slow time.
And the fact that it is 2 independent ODEs, that comes from the models. Is the model taken 2 independent ODEs?
That at the outset we're saying, there's a fast response and a slow response.
Okay.
And this also comes from some energy balance modeling work. So, I mean, there's some ontological relevance to this, right? So you think of climate feedbacks in a global mean sense,
okay,
right? And you can show that the global mean radiative response or the global mean feedback is to a good approximation related directly to global mean temperature. And so then we're really thinking about global mean temperatures with a fast response comprising the fast subsystem, and that's interacting with the slow subsystem, which is the deep ocean, right? And the deep ocean interacting with the fast subsystem gives us the 2 time constants. Which
so the fact that we know that atmosphere and ocean has different levels of response, difference in response, that gave the intuition for model, and that is what is reflected here.
So there's some intuition that there are these 2 different time scales involved, and so we go in and build in these models for
thank you.
The global mean climate response in terms of 2 ODEs. Yes. And so the question then is, how do we think about this? And before that, I should point out that owing to the integrals, it's history dependent, right? So f of t, f depends on cumulative emissions, airborne fraction of cumulative emissions. And therefore, the temperature, the global warming response depends on time. It depends on airborne fraction. It depends on cumulative emissions. It depends on the past history of airborne fraction and cumulative emissions. And I'm going to gloss over the details in this talk, but just give you a schematic view of how we think about this. Imagine it were just dependent on the airborne fraction and cumulative emissions. And under what conditions would this function be independent of the emissions pathway and just a path-independent function of cumulative emissions? And the answer is, well, between time t, so imagine these are contours, these are just for representative purposes, please don't take these literally. The change in temperature between time t, small t, and small t plus delta t is determined by the change in cumulative emissions. And this requires that the change in temperature is approximated by the directional derivative along the axis of the cumulative emissions. And this entails certain inequalities. There's a complication to the story. We also have to account for the effect of the history of the airborne fraction and cumulative emissions. And when you do all that, the answer is there's some simple high school algebra. And when one does all that, the answer is very simple. Path independence occurs if the timescale for the cumulative emissions to change is much smaller than the timescale for the airborne fraction to change, and also small compared to this quantity tau sub d. And this is why I highlighted tau sub d in the previous slide. But here in our talk, we're going to talk about this relationship between tau r and tau n. Right? So in other words, path independence occurs if the airborne fraction evolves slowly on much longer timescales compared to the timescales for the evolution of cumulative emissions. And these are linearized timescales. What do I mean by the cumulative emissions timescale? It's a time it would take for the cumulative emissions to grow by a factor of e if it were constant. What's the airborne fraction timescale? It's a time it would take for the airborne fraction to decrease by a factor of e if it were constant. But of course, these are constantly changing in time. And indeed, what one sees is a disparity in the timescales, right? So for instance, it takes centuries for the airborne fraction of CO2 to decrease by 50%, correspondingly to increase by the same factor of 2. It only takes decades for the cumulative emissions to double. And this is because this disparity is partly also because of the time scales of the emissions cycle, how long it takes for the emissions to increase and decrease. but it also has a lot to do with the slow processes in the Earth system carbon cycle. The slowness of certain components of the Earth system carbon cycle ensure that the airborne fraction takes centuries to decrease by a factor of 50%. And then we can ask, well, what if we were to turn off the slow processes in the carbon cycle, make carbon dioxide in the atmosphere behave like methane? And well, the first thing that you would see, obviously, is CO2 in that case would not accumulate and global warming would be less. But also, you see that global warming is no longer a path-independent function of cumulative emissions alone. And this is because in this case, the airborne fraction decreases more rapidly on timescales that are comparable to the timescales of the evolution of cumulative emissions. Let's quantify this. We're computing those linearized timescales, right? But these are functions of time. So at each instant, the airborne fraction timescale is how long it would take for the airborne fraction to decrease by a factor of E if it were constant, right? From that point on, and correspondingly for cumulative emissions, except with cumulative emissions, we're talking about the increase in cumulative emissions. And you see that with a correct carbon dioxide model, the airborne fraction timescale is an order of magnitude longer. And correspondingly, the airborne fraction evolution is an order of magnitude smaller. The rate of, so an order of magnitude slower. And if CO2 were to behave like methane, the airborne fraction timescale would be much shorter. It would be not short enough, not long enough, and the effects of airborne fraction of CO2 would no longer be negligible. That is, the effects of differences in the airborne fraction of CO2 between different emission scenarios would not be negligible, and path independence would not have occurred. Yes.
May I ask, in the actual Earth systems models that people run, is it the case then that the airborne fraction does live for much longer than that is, the time scale is much longer than that for cumulative?
Yes.
About an order of magnitude?
About an order of magnitude, yeah, about an order of magnitude. Right? So here's a simple model which doesn't get the right airborne fraction, but it gets the time scales because you have the slow processes in the carbon cycle.
I see.
And like Professor Saravanan mentioned yesterday, about half of the CO2 is taken up very quickly by the terrestrial biosphere and the oceans. And so the airborne fraction of CO2, there's a very nice diagram of the airborne fraction of CO2 in the latest IPCC report. I don't have it here, but it's roughly about 40 to 45%. And there's, of course, natural variability having to do with, variation in uptake of CO2 by the oceans and so on. But roughly, it's about 40, the rule of thumb is it's between 40 and 50%.
Okay.
And that's very slowly varying because the airborne fraction doesn't evolve very quickly, right? It evolves on time scales that are centuries long.
I see. And then, sorry, just to absorb the main lesson of your model, which is, so this lesson that it's independent, that the global warming is independent of the pathway and just dependent on the total cumulative amount, is also borne out in actual model Earth systems models. Can we test it there just to see?
Yes. So the first graph, right? So proportionality implies path independence. The converse is not true, of course. And so we're looking at the more general problem of path independence. Yeah? Thank you. Yes.
If CO2 emission, cumulative emission of CO2 is doubling every decade or so, then how is the airborne fraction staying the same? Because you said it takes centuries for the additional CO2 to deplete.
That's a very good question. There are fast processes and there are slow processes. Right? So the fast processes ensure that within about a decade, half of the excess CO2 ends up in the surface oceans and the terrestrial biosphere. The slow processes have to do with rock weathering, reducing the acidity of the ocean, mixing of the CO2 that's in the mixed layer of the upper ocean into the deep ocean. All of these are very slow. Right? So I think that's a very simple physical argument that gives rise to the rule of thumb that the airborne fraction of CO2 is roughly 50%. All right, but of course, I think there's, when you put in the time scales into an impulse response model with a few different time constants, there's much richer dynamics. But the upshot of it all is that the airborne fraction is very slowly evolving. It may not exactly be 50% in these in the simplest models, but the simplest models nonetheless show that the airborne fraction evolves very slowly. And so, we've seen that for path independence, the timescale for the evolution of cumulative emissions must be much shorter than the timescale for the evolution of the airborne fraction. We can look at this further, and it turns out that this ratio which has to be small, is directly related to the following dimensionless parameter. It's the ratio of T over tau. What is T? It's the time. So imagine you have an emission cycle that goes up and comes down, as we do in policy studies. And so this is T, the time it takes from the start of the emission cycle to the end of the emission cycle. And tau is the atmospheric lifetime. And so in order for this to be 1/10 or smaller, roughly T over tau has to be less than or equal to 1. Right? So the emission cycle has to play out over a time period that is either comparable to or smaller than, not much smaller than, but comparable to or smaller than the atmospheric lifetime. And this is for a different given shape of the emissions curve. Of course, if you make the emissions curve more sharply peaked, this curve moves to the right. And that's something that one can understand. It has to do with how the peakedness of the emissions curve affects the cumulative emissions timescale. And essentially, what does it do? It increases the growth rate of the cumulative emissions and thereby reduces the cumulative emissions timescale. And so the blue curves, which are more sharply peaked, shift further to the right. But that's not important to our account. It just means that if you want to understand in a counterfactual sense why we're having this conversation about cumulative emissions budgets, we're having this conversation about cumulative emissions budgets for CO2, and by extension, one can have the conversation about cumulative emissions budgets for other kinds of forces where a condition such as this holds, right? So where the emission cycle is playing out over a time scale that is comparable to or smaller than the atmospheric lifetime. And where does this come from? Some very simple analysis. I'll very quickly run through it. The expression for airborne fraction, which is the airborne fraction of cumulative emissions, right? The excess concentration of CO2 where C equilibrium is a pre-industrial equilibrium divided by cumulative emissions. One can write an expression for the airborne fraction timescale, close the equation by having an expression for the evolution of concentration, and then we simply rescale time. So these familiar weighted integrals where you typically have T in years divided by the lifetime in years is rewritten as T over big T times big T over tau. And so then you recover this quantity that we're interested in. And it also hints that this relationship depends on where you are in the emission cycle. And we can go a bit further, and ultimately we find that this ratio is here. So if I put in, alpha equals a very small quantity, T over tau, say alpha equals 0, this quantity is 0. And so the cumulative emissions timescale is practically negligible and path independence is nearly exact. But of course, alpha is not 0, but it's some quantity. And we can find that this tau m over tau r has to be, in order for this to be small, alpha, which is T over tau, has to be roughly less than 1. Right? But it also tells us something about the structure of the problem. It tells us that—
Hello, sir. This is I'm from IIT Bombay. I just wanted to say, if it's aerosols, is the alpha value 0? Because CO2, you said it's a significant value. If it's aerosol, because the life cycle is a lot shorter, so then the path dependence is—
Yeah, let's look at that, right? So what's in the denominator? The denominator has the atmospheric lifetime. So an aerosol with an atmospheric lifetime of about a week, and you're thinking about an aerosol that's being emitted for the last 50 years. Alpha would be pretty large, wouldn't it? Right? So then—
Right. Yeah, okay, got it. Emission cycle period is large and the atmospheric lifetime is low.
That's right, yes. Yeah.
Okay.
So path independence typically occurs, right, in this model when something plays out very quickly in comparison to the atmospheric lifetime. But we also see that it depends on the position of the emission cycle, and typically this quantity goes up. It should be small for path independence, but it goes up as X increases. So it tells us that in the beginning of any emission cycle, you're going to have approximate path independence. As you also see for methane, question is, do you have it at the end? In the peak and decline phase where X is between 1/2 and 1. And the answer is that requires alpha to be smaller, roughly smaller than 1. So here's how the cumulative emissions timescale evolves in time. So remind you, cumulative emissions timescale is the inverse of the growth rate. And so it's cumulative emissions over emissions, or an emissions curve shown on the top. The bottom shows, the blue curve shows the evolution of the cumulative emissions timescale. And we see that this is increasing in time. And so the cumulative emissions timescale really typically increases it with time, and it's fairly large and compared to the other timescales when emissions are small in the decreasing phase, not in the increasing phase, because in the increasing phase, cumulative emissions has not accumulated. So cumulative emissions is growing together with emissions. In the decreasing phase, cumulative emissions has accumulated, emissions have come down, so the cumulative emissions timescale grows up. In other words, it's hard to grow cumulative emissions any further. And this has the kinds of implications we'll discuss. For instance, if you consider scenarios where the emissions are not zero, but they're small, you're moving cumulative emissions, but the timescale is still long. And so the effects of other factors cannot be neglected. Right? So cumulative emissions is changing. It's not unchanging, but it's changing rather slowly. And this is where path independence can fail in this regime. And so a number of studies have examined this and examined, for instance, hysteresis in the presence of net negative emissions of CO2. This kind of simple model analysis is no substitute for the kinds of Earth system model studies that include, understand, examine the implications of these feedbacks in the terrestrial carbon cycle and the ocean's carbon cycle that give rise to a path-dependent response. But these kinds of studies do point to where that path independence comes about. Right? It comes about towards the end of the emissions cycle when the cumulative emissions timescale is rather long. And therefore, the effects of the other factors can no longer be neglected. Another point I want to make is you consider, two emission scenarios, one which is small, one which is negative, and then you can consider the path independence errors, and they're highly correlated because they come from the same physics, right? So again, while this is no substitute for the kind of Earth system modeling needed to understand the distribution of the hysteresis response, we still know that whether or not one considers small but persistent emissions because you're trying to decarbonize air transport and steel and cement and you're unable to, or it's difficult, and so you're going to have to deal with a long tail of persistent emissions even after decarbonizing much of the economy, or you have negative emissions which are not zero and therefore you're moving along the cumulative emissions axis with a path-dependent response, the errors to our best understanding appear quite related because they all have to do with the thermal inertia of the system. That being said, these simple models don't do justice to the distributions that you will get in more complicated models. There have been a few modeling studies of this path-dependent response, and they seem to suggest a distribution of the kind of hysteresis response that's quite different from the simple models. So it's clear that the simple models seem to underestimate the inertia in the system. So I'm going to, before I conclude, I'll just give a quick couple of examples. One is where we examined the implications of this kind of analysis. You consider a case where you have slow mitigation of, say, a hydrofluorocarbon. These HFCs, for example, replaced CFCs, the ozone-depleting CFCs following the implementation of the Montreal Protocol. And if you consider a case of slow mitigation where here I think the atmospheric lifetime is about 50 years, so you consider a case of slow mitigation where the time period of the emission cycle is much longer than the atmospheric lifetime, then you obviously don't have a path independence response. And if you were to have rapid mitigation, right, you have a path independent response. And of course, this kind of analysis also carries over to considering baskets of CFCs with similar mean lifetimes. I also want to present another counterfactual story to understand what this means for CO2. So imagine you had CO2 had an atmospheric lifetime of 100 years, which we know is too short. It's actually time varying. It's increasing with time because over time, the slower processes tend to predominate, but it's definitely much larger than 100 years. So this is an underestimation. You will not get path independence, right? Unlike in the earlier figures, the way where we saw path independence, even in the simplest models. If the emission cycle had evolved more slowly, right? Instead of evolving, say, over a few hundred years, it evolved over a millennium, then the path independence relation would fail more severely. But on the other hand, even with a lifetime of 100 years, if the emission cycle had played out within 100 years, then the path independence relationship would have been approximately valid during the global warming phase, which is really what we're interested in. So I'll summarize this part by noting that why are we interested in this? There have been a number of studies seeking to explain the origins of proportionality. And that typically, one way to think about it is proportionality comes from some dimensionless parameter being close to 1. And there have been a number of studies that have explained the how of this relationship, right? There are things, for instance, the logarithmic radiative forcing relationship is balanced by the diminishing ability of the oceans to take up heat and CO2 as the Earth system warms. But we can't explain the why question. But insofar as all we need is path independence for cumulative emissions budgets and not a particular relationship, not proportionality between global warming and cumulative emissions, it seems like a question that is based on explaining why something is very small. Why is the ratio between the cumulative emissions timescale and the airborne fraction timescale small? Is more amenable to not only answering the how questions, but also the why questions. And the answer is quite simple. The cumulative timescale is a few decades long because we're largely considering emission cycles that are playing out over a couple of centuries. Even though we date the Industrial Revolution to the 1700s in various phases, if you look at the emissions curve, it really began to rise in earnest in the early 1900s. And so we're thinking about emissions curves that largely play out between the 1900s and this century. And then there's a distinct relationship between that and the cumulative emissions timescale that makes the cumulative emissions timescale a few decades long. And we know there are slow processes in the Earth system carbon cycle, which make the airborne fraction, a few centuries long, the cumulative emissions timescale being a few decades long. And this means that changes in cumulative emissions drive global warming, and new temperature contours are picked by these changes in cumulative emissions. This is no longer true towards the end of the emissions cycle, where the cumulative emissions vary slowly and it's no longer the dominant effect. And that's when differences in the airborne fraction between different scenarios, right? Differences in the airborne fraction between different scenarios start to matter to the global warming cumulative emissions relationship. And it's really these scenarios. And this also accounts for why, in scenarios with persistent but non-zero small emissions is where we have to worry about path dependence. But if we're not concerned about that state of the world as yet, if we're only concerned with the peak and decline phase, we don't have to worry about higher order effects on the global warming cumulative emissions relationship because of our confidence of this separation of timescales, right, between the cumulative emissions timescale and the airborne fraction timescale. Owing to well understood and very simple physics that occurs robustly across a hierarchy of models and that doesn't require the most complicated Earth system models, but of course is persistent in the most complicated Earth system models. So this is the first part. I'll stop here.
Sorry, Ashwin.
Yes.
I can just ask you, I thought I was following till the last few points. I mean, I was thinking like this, but please correct me. If the airborne fraction stays around for a very long time, then, it's hanging around while the cumulative emissions are changing on a much shorter time scale. So the temperature is responding just to the fraction which is hanging around, which is changing very little. And that's why it doesn't matter how the emissions occurred, because what's important is that they are produced and then they hang around. Okay, intuitively, it seemed to make a lot of sense. But then if the emission rate also slows down, does that, towards the last 2 points of yours, does that change things so much? Because, I mean, are we interested in the temperatures also changing on the cumulative emission timescales? Because then I can understand that the airborne fraction and cumulative emissions are, say, of the same timescales, and we are interested in computing temperature changes. Then, of course, this approximation won't work. Was that the thing? Or, I mean, if we are interested in temperature changes on smaller time scales than both, then of course, I suppose it doesn't change much. Is that what happens?
So we're interested in, say, temperature change on decadal time scales.
Okay, so that's fixed.
Let's say we want to understand what happens up to the end of the century.
Okay.
Now, in order to understand what happens up to the end of the century, you want to understand the fate of CO2 in the atmosphere to the end of the century, its effects on radiative forcing, right, and consequent consequent effects on global warming. Right. Now, turns out there's an emergent, so in principle, we'd like to understand all the links in the chain, but there's an emergent simplicity given that global warming is a function of cumulative emissions. So if I want to know what happens in 2100, I need to only understand cumulative emissions until 2100. Right? So global warming in 2100 from pre-industrial times will be some function of cumulative emissions until 2100. And so we're interested in global warming and cumulative emissions on timescales, on century timescales. But that in turn is influenced by the disparity in the timescales between cumulative emissions and the airborne fraction. And just another way of thinking about rates.
Sorry, just to say, why is it that when cumulative emissions start varying slowly, then your path independence fails? I didn't quite get that.
That's because when it starts varying slowly, this happens. It approaches these other timescales. Yeah, so the point is, anytime the cumulative emissions timescale is no longer short compared to the timescale for the evolution of the airborne fraction, differences in the airborne fraction will start to matter. Right? And if I consider, yes, yeah, that's right. So if I'm interested way up until 2100, and I consider scenarios which are peak and decline, but nonetheless not zero. On this timescale, I'm interested in temperature evolution. Yes. So it's all the same time scale. It's all the same time scale, yes. Yeah. So our horizon is different from the time scales itself, but the time scales impact what is consequential in our horizon. Yes.
Now we're assuming that there's two time scales, right? So, but in the real Earth system, there's, okay, water vapor may be too short to worry about. But what about ice melting is that short? And what about the all kinds of timescales in the ocean? So if you account for all that, will you still have path independence?
Yes. Yes. So you're talking about the different climate response timescales, right? Yeah. How
the airborne fraction is now hanging around at some constant value. The ocean may take time to respond.
Yes.
So then like that may not have path independence anymore, or it's not obvious to me.
Yeah. Yeah. So clearly this model is this model has three variables. One is time, one is cumulative emissions, and one is the airborne fraction. So under what conditions can you neglect the effect of changes in or differences in airborne fraction compared to cumulative emissions, changes over time? And that answer comes from comparing your airborne fraction to your cumulative emissions timescale. But are there factors that we've neglected in the model altogether? It's possible, but as far as comparing emission scenarios with different time periods is concerned, right? The predominant effect that has is on the cumulative emissions timescale. And as far as comparing different forces with different atmospheric lifetimes is concerned, the predominant effect that has is on the airborne fraction timescale. So if one wants to understand this problem, the answer lies in the relationship between these two timescales. But certainly there are, conceivably there could be climate feedbacks and so on, which could undermine path independence. Yes. Oh, we don't think about it. So temperature is always changing, right? At any given time horizon, so temperature is a continuous function of T. Of course, there are two time constants in this problem. But at any given time horizon, the temperature will be an approximate function of only cumulative emissions if over that time horizon, cumulative emissions is a dominant factor. So in principle, you could write down, right? You could sketch the airborne fraction timescale, the cumulative emissions timescale. And as long as there's a disparity between the two, throughout that time horizon, temperature will be a function of cumulative emissions. But if then you want to ask what are the timescales with which the temperature is changing, depending on what one means by that, one answer to that question is, well, there are these two time constants in the temperature response. Right? There's a slow time constant and a fast time constant. And so it's changing on the time scales of radiative forcing, because on decadal time scales, T is approximately in equilibrium with F. And it's also changing on these really slow time scales, which are governed by the slow climate response. Yeah. Any other questions?
Sir, I'm online. So just a comment. So the fast response and the slow response that you put in your equation, the slow response is generally the temperature generally scales with radiative forcing at the top of the atmosphere. But the fast, so the radiative forcing is calculated for the atmosphere as like a top of the atmosphere minus the surface, and that is what scales with the temperature. So the slow generally agrees well with any species that we take, CO2, carbon, black carbon or sulfate or anything agrees. The slow response is sort of consistent amongst models, amongst species. But the fast response sort of has issues that where is the carbon dioxide that is emitted, or where is the black carbon that is emitted, which is the layer that accumulates and stuff like that. Because it acts on a faster time scale, there are associated problems with it. So the overarching question is, can this model be applied to aerosols and other short-lived species?
Yes, the assumption of the model is that there are two time constants. And the model is an idealization. It's an idealization of the energy balance of the Earth system with a fast response and a slow response. If you were to look at, there have been efforts to fit these kinds of models to simulations, very idealized simulations of the more complex Earth system models. And you find that there's a lot of uncertainty in all of the parameters. All right, so there are 4 parameters. There's the heat capacity, there's the fast time constant, there's a slow time constant, and there is this tau d. And all these parameters turns out very uncertain. And in thinking about what gives rise, what is the main contribution to the intermodal differences in the long-term climate response, it turns out that the parameters of the slow response are quite consequential. So while you can apply this model, understanding its limitations and understanding, of course, it doesn't give you spatial information, it tells you something about the global mean energy budget and the global mean temperature response. The models these simple models, of course, have to be interpreted with caution. And the fact is that all of these parameters are uncertain. The slow parameters are equally uncertain. It turns out that the coefficient of the slow response is as uncertain. So it varies between a few hundred years to a few thousand years, right? So, and that's because the inverse coefficient, the parameters that go into estimating the inverse coefficient of the slow response are also very variable. So if you were to do, say, an ensemble simulation using this model, you'll find a large spread, no matter what species you're concerned with, right? But how would you translate any species and run it through the model? You would estimate radiative forcing and assume that it's the kind of forcing that that constitutes the definition of the forcing in this model, and you would run it through the model, and you would, get, but you would get a large spread as a result. Are there any more questions on this part? Then I can move on to the, yes? All right. So here's a diagram from a paper in 2005, which showed that monsoons can respond sensitively to, in fact, discontinuously to small changes in forcing. This diagram is called the bifurcation diagram. It shows the mean precipitation. You can think of it as a seasonal mean precipitation in a system of ordinary differential equations, describing the model in that, the monsoon in that model. And the upper branch shows the monsoon as we know it, As you increase the planetary albedo, the mean precipitation declines until you reach point B1, at which this branch disappears, and to the right you're left with a branch with very little to no rainfall. And this study was the basis for including the Indian monsoon among tipping elements in the Earth system. Here's a quote from that paper. The land to ocean pressure gradient, which drives the monsoon circulation, is reinforced by the moisture the monsoon itself carries from the adjacent Indian Ocean, and consequently any perturbation that tends to weaken the driving pressure gradient has the potential to destabilize the circulation. Here's a quote from a paper, actually from the abstract of a subsequent paper, which sought to identify the basic mechanism for this transition. Though details are complicated, observations reveal a defining moisture advection feedback that dominates the seasonal heat balance and might act as an internal amplifier, leading to abrupt changes in response to relatively weak external perturbations. And the paper presents a minimal conceptual model. Here are the equations. I won't get into the details of the equations. I'm going to provide an interpretation, but here's the basic mechanism. You have landward winds. So here are these monsoonal winds, which bring moisture. The moisture condenses, it heats up the atmospheric column over land, further driving the winds, right? And that's the moisture advection feedback that was being referred to here. Here's a quote: the abruptness of the transition emerges through an additional stabilizing effect of heat advection, which is cooling the atmospheric column and also reduced for reduced monsoon winds. So in this model, the bifurcation comes from interaction between the destabilizing effect of moisture advection, the moisture advection feedback that's being referred to here, and the nonlinearity of temperature advection, which cools this column. And we'll see a way to think about that in a moment. But I'm going to provide our view of how we think about this and then discuss some consequences for nonlinear dynamics. We're imagining this atmospheric column over land, analogous to this. Typically, there's convergence below, there's divergence above, and we examine the evolution of a quantity called the dry static energy within this column. Here's the differential form of the dry static energy balance. This is dry static energy. It's basically temperature plus height, right? It's a measure of height and measure of geopotential. G is gravity. CPT is a measure of temperature. And we integrate over this volume to get an evolution equation. This is a one-dimensional ODE. X is the land-ocean temperature contrast. It's not the surface temperature contrast, it's the contrast in the column mean, the temperatures of the column mean temperatures and the differences between the land and the ocean. And here's the evolution equation, radiation. I won't get into the details of the terms, but this term corresponds to the moisture advection feedback. This term corresponds to the nonlinear advection. And it turns out that what's true of the dry static energy is as you go up in the atmosphere, the dry static energy increases with height. And that's because the lapse rate, the vertical gradient of temperature, is smaller than the dry adiabatic lapse rate. The dry adiabatic lapse rate is Cp over G. All right, and so as you go up in the atmosphere, the lapse rate is always smaller than the dry adiabatic lapse rate, and therefore the dry static energy increases with height. And therefore, circulations which have convergence below and divergence above export dry static energy. But this export is through two contributions. There's a contribution that is quadratic in X. So this comes from advection. This corresponds to horizontal advection. But there's also a term that is linear in X. So there's a term that's linear in X, and this comes from vertical stratification. The idea that to first order, the stratification, the vertical gradient in dry static energy doesn't depend on the horizontal winds. And so you end up having a term that's also linear in X, and X is just a measure of the strength of the monsoon circulation or the wind speed. And it turns out that the accounts of monsoons as tipping points focused on this horizontal advection term and neglected this term. And this makes all the difference to conclusions about whether monsoons are tipping points. Just a very quick primer. I'm sure you're all familiar with this. We consider conditions for bifurcation or their absence. We're concerned with steady states and how they change when you change the parameter. This is an evolution law. X is a state variable, alpha is some parameter. And we see that if you change alpha, X varies continuously with alpha as long as this condition is not met. It's also equivalent to the eigenvalue of the steady state. Therefore, bifurcations correspond to the vanishing of the eigenvalue of the steady state. And if you go back to the governing equation, then we look for bifurcations or their absence by looking at contributions to the eigenvalue. And so it turns out that this moisture advection feedback, the central destabilizing effect in the previous accounts of monsoons as tipping points, increases with X. It's a positive contribution to the eigenvalue. This advection, this advective effect is a negative contribution to the eigenvalue, and so it increases in magnitude with X. And our search for bifurcations then reduces to looking for points where this contribution and this contribution to the eigenvalue balance each other, because it turns out that these terms don't depend very strongly on X. So here's the case without vertical stratification. The red curve describes the negative contribution, the green curve describes the positive contribution, and the bifurcation points are where these curves intersect. And if you don't include the effect of stratification, the vertical gradient in dry static energy that corresponds to this term, you're going to get a bifurcation point. A bifurcation point is intrinsic to the model, and the reason for that is monsoon steady state is stable. In order for the steady state to be stable, the stabilizing effect, right, which here is the red curve, must be larger than the destabilizing effect. And so the monsoon equilibrium lives somewhere here, but that stabilizing effect vanishes because it's a quadratic term. So the slope of the quadratic term goes to 0 as you approach the origin, and so there must be a bifurcation point. But if you were to include the effect of stabilization, you basically push the red curves away from the origin, and you can or cannot get a bifurcation. In other words, the bifurcation is no longer intrinsic to your system of equations. But if you were to do a Monte Carlo simulation and fit parameters to the data and so on, you'll see it's very unlikely that there is a bifurcation in this system of equations. And the corroborative study, 2 studies came out around the same time. This with a very different model. Here's a quote here. It's shown that the theory used to predict such tipping points omits a dominant term in the equations of motion, and that both a corrected theory and an ensemble of climate model simulations exhibit no abrupt shift in response to large changes in forcing. And so this is the case without vertical stratification, this dominant term. This is the case with stratification. And as you can see, there is no bifurcation here. So the question is, how is there no bifurcation, even though these equations are nonlinear? And there's some ongoing work led by my colleague showing that really there's an exchange of relevance of solutions. So where the monsoon regime, we're concerned whether with the net column energy input R being positive and corresponding precipitation, seasonal mean precipitation being positive, that solution has to be spliced together with another solution for the non-monsoon regime. And you do have, turns out you do have a bifurcation in the non-monsoon regime, but not in the monsoon regime. And that's because of the dominant stabilizing effect. So when you're in the monsoon regime, you have convergence below, divergence above, dry static energy, and its thermodynamic analogs. People talk often about a quantity called the moist static energy, which includes the effect of latent heat. So you just add LQ to these equations. Right? And one comes to the same conclusions because the dominant balance in the dry static energy and moist static energy equations come from the vertical stratification of these quantities, and the vertical stratification of both the dry static energy and the moist static energy come primarily from this effect, right? And which arises because the vertical lapse rate of temperature is smaller than the dry adiabatic. And so they all basically export energy. And so you don't get a bifurcation in this regime. And when you splice these two solutions, the nonlinear advection gives you a bifurcation in this regime. But of course, that's not physically relevant because the values of R are roughly bounded between about -50 watts per meter squared to about 150 watts per meter squared. So just an interpretation of, there is nonlinearity, and the presence of nonlinear advection was the intuition that gave rise to thinking about the role of potential role of nonlinear advection in generating tipping points in monsoon models. And indeed, it does play a role, but there's no physically relevant bifurcation. And so by all appearances, the monsoon does not appear to be a tipping point. And so the community seems to be revising its view on that. But since Professor JS mentioned just in my last slide, he noted this work on rate-induced tipping. I'm not going to discuss this in this talk. This is just my last slide, just to point to anybody's interested in this. They can perhaps begin with this paper. And the question of rate-induced tipping is quite different from bifurcation-induced tipping. So here's a nice classification of the kinds of tipping points one can get in nonlinear systems. And there's, of course, the very familiar noise-induced tipping. There's the bifurcation-induced tipping. Rate-induced tipping is different, but it's very relevant to slowly varying systems. And you're not really crossing a bifurcation point, but you're really, in some sense, pulling the landscape, the basin of attraction, from underneath the system. And if the system has enough time to then find that it's not living in a basin of attraction, it just moves away, as shown here. And so that's very relevant to, for example, problems like the meridional overturning circulation and so on, where you may have a forcing on faster timescales, on decadal timescales, but the response may take a long time to catch up with the forcing. So this is a very interesting area of work, and I think the literature in the community of folks who work on dynamical systems is very rich, but I think the climate science community at large is only beginning to come to grips with it. And I think one reason for flagging this by Professor JS yesterday was that this does not seem to be highlighted in its implications for mitigation and the climate change problem on decadal timescales, especially vis-a-vis these slowly varying systems, which take time to catch up to changing forcing, hasn't nearly been understood or highlighted to the fullest. So with that, I'll stop, and I can take any questions that any of you may have.
Thanks a lot, Ashwin. That was a really great talk and emboldens someone like me that you can try to do something with these very, very nice models. But just if I can ask you about this, because I didn't quite understand what you were saying about the rate tripping cases. But let me go back to Professor JS's talk, where he talked about this Atlantic meridional circulation and how that could have a tipping point. So that lies in the same class as these rate dependent, or no? That's something. Yes, they do.
Yes. So
Okay.
the difference is, for example, if you have a system which is slowly adjusting to slowly changing forcing, then it can cross a bifurcation point.
Yeah.
But if the system doesn't have time, so with a bifurcation-induced tipping, you're actually changing the landscape, right? So imagine you have a potential well, two potentials, two wells. And then the two wells disappear and they merge very slowly.
Right.
And the system is actually at the minimum of the potential well. What does that mean? The system is adjusting fairly rapidly to the change in the landscape.
Yes.
So there's not that much of, or rather the system response timescales or adjustment timescales are rather quicker than the timescales with which the landscape itself is changing. So typically you get a bifurcation-induced tipping with a slowly varying parameter where the system response timescales are fast.
Right.
So if I have two wells, two
Yes.
steady states separated by an unstable state,
Yes.
and I'm changing parameters such that those two steady states merge,
Yes.
that's one way to get bifurcation-induced tipping.
I see.
Right? I make one unstable, and then it slips into the other potential well. But if the state is always in the minimum of the corresponding potential well, I'm assuming that the state adjusts rapidly enough. Typically, this occurs if there's a separation in timescales between the deformation of the potential well and the system state response.
Correct.
Right? But
And then
rate-induced tipping is different. I'm in one minimum, but I've quickly pulled the attractor from underneath. The system is still there, but then that's no longer the potential well that used to exist.
Correct.
I can re-inject it. For instance, I can reverse the freshwater forcing, for example, in our problem. then the system stays there. If the system has long enough memory, if that system inertia is large enough compared to the timescales of the anthropogenic influence.
Sorry.
So in some sense, the timescales are reversed. So the forcing is rapid. The change in parameters is rapid. The system has a lot of memory. Then you're liable to get a rate-induced tipping. But you can also get a bifurcation-induced tipping in such systems. But
I see.
The concern is that you don't have to wait for a bifurcation point in the overturning circulation if the rate of freshwater forcing were large enough.
But sorry, you said it just now, but I understand the first case because it's something very familiar in physics where you solve for the fast stuff given the background, and then your background changes, but each time step you. But when it's rate induced, you say it's the other way around. Is it that? Did I understand that the underlying potential changes much more rapidly, and this is like the response is just frozen because it can't adjust as fast.
That's right. Yeah. So
and then where's the
occurs in the slow system, right? And the background occurs in some sense in the fast system.
I see. So the background moves very fast. The system is frozen, but then it evolves slowly and in some sense undergoes a bifurcation. Is that right?
There's no bifurcation.
There's no bifurcation.
There's no bifurcation.
I see. But it just remains frozen in that sense, in the state it was in. Eventually it changes.
When it starts, when it starts to adjust, right? Let's say it's following a 1D gradient system. It's following a gradient, but the gradient has changed.
Yes. So then it just follows
a gradient on its own time scale.
Okay.
And when the landscape has changed, it moves somewhere else as a result of that.
I see. And that would account for the meridional phenomena he was talking about, just this fact that the so to say, the potential suddenly changes and the oceans have to respond to that.
Yeah, so I think the point being that there've been a couple of papers showing the importance of this for the overturning circulation, and thus far, and which means you can have things happening on century, sub-century timescales in these simple models. You don't have to wait for hundreds of years for a bifurcation point to be crossed. It takes time in a slow system to cross a bifurcation.
But sorry, why is this surprising? This potential moves very rapidly.
Yes.
Then the system will then just be frozen during the change.
Yes. Yes.
And then it evolves on its own time.
On its own time. In response to the new. Yeah, it goes up instead of coming down. Right? In this illustration from I think this reference. Yeah, it's very intuitive. It's very intuitive. I think in some sense, it's not conceptually novel. It's just that in the traditional discussion about tipping points, including in Earth system science, we've always been talking about bifurcation-induced tipping. So not only is that tipping point literature and the documentation of tipping elements of the Earth system largely about those that are vulnerable to bifurcation-induced tipping, but also these cascade effects that were part of the discussion yesterday. All of this is new, including rate-induced. So if one were to catalog possibilities for rate-induced tipping, perhaps one would come up with a new list of phenomena that, of course, include, but are not limited to those previously listed ones. I think that's the point. But this is very new, I think, on the timescales of the community. And so I think it has not made its way, it has not percolated to the wider context.
Sorry, I'll stop, but just to ask you, I mean, typically in the kind of physics that I know, either the potential would move much more slowly and the particle move much more rapidly. So that was the first case, or the other way around, which would be the second case, or they would be at about the same time scale. And then sometimes you can get interesting phenomena like resonances or something. And is there an analog of that here? People thought about it here, or is that not? Just, I'm sorry, this is a vague question.
Where the parameter say moves to the same time scale as the system. It's very interesting. I don't think it's been cataloged here. So I think that's definitely something to think about. So I think these two extreme cases are where there is a clear separation between, right? There's obviously noise-induced tipping, but that's not parameter-induced. So there's some fluctuation within a potential well that might be resonating with some threshold frequency of getting the amount of noise you need to tip. But resonance between timescales of parameter variation and the timescales in the system is not part of this catalog. And I think there might be work to be done there.
Okay, so people who are attending online, if your curiosity has reached a tipping point and you have a question, please go ahead at this time. Okay, so anybody offline? Yeah, go ahead.
Hello. Yeah, so I'm just trying to map what you said to my understanding. Let's say I have a magnet, and if it's a paramagnet, there is a potential, and if I heat up the magnet, it goes from a paramagnet to a ferromagnet. And in that case, if I look at the potential to this, or not the potential, let's say to the free energy of the magnet, it transitions from a double well potential to a single well potential. And if the spins on the magnet respond fast enough, it goes from a paramagnet to ferromagnet. In your, in the way you presented, would you call that a bifurcation or a?
That's a bifurcation.
That's a bifurcation. Okay, and now I was a bit lost. How is that connected to the monsoon, Indian monsoon that we had?
So the question was, so I'm sorry I didn't present the physical intuition behind this, but the idea of this account of the monsoons is that owing to the role of nonlinear advection in stabilizing the monsoons,
right,
there is some minimum velocity, and in these models, velocity is a proxy for strength of circulation. And the simplest models say the following: I'm going to convert some moisture, and all of it rains out.
Okay.
So there's a very simple relation of proportionality between the strength of the monsoon and strength and amount of precipitation, say seasonal mean precipitation. So the idea being, my stabilizing effect on the monsoon is nonlinear. It's not only nonlinear, it's quadratic, because it relies on horizontal advection of horizontal gradients of dry static energy.
Right.
For example, or moist static energy, if one were to go that route.
Okay.
Include the LQ term in the equations. Right? And so there's some minimum velocity below which it's not possible to stabilize a monsoon, and the monsoon cannot exist.
Okay.
That's the idea. And so that gives rise to saddle node bifurcation model. So that was the basic intuition. But then the moment you put in the, consider as you must, and as all models do. So the difference between these simple idealized models and the real models is the real models have things which we may choose to include or not in the simple models, and or better or worse, right? And so if the thing that you choose to not include is a dominant stabilizing term, which comes from the vertical gradients in the dry static energy, you've thrown away the dominant stabilizing term, which doesn't lose its strength as you weaken the circulation, because it's a term that's linear in X, linear in the state variable, and that slope and that contribution to the eigenvalue doesn't diminish even for weak circulations.
So the potential here is the gradient that advects the water vapor up.
What's the gradient? I'm sorry.
You mentioned a moisture gradient.
The moisture gradient.
Yes. So I'm trying to understand what is the potential here that drives the monsoon, which is changed when the bifurcation happens.
That's an interesting question. Yeah, so the potential would come from this equation, right? Potential would come from this equation.
Okay, I'll be honest, I don't have an understanding of the equation, but is there a physical interpretation of the potential?
That's a very interesting question. I don't have an immediate answer. I will think about that.
Okay, thank you.
Thank you.
So I was very relieved to know that, stratification is being our guardian angel, and monsoon is going to be preserved.
Yes.
So like this started me thinking, we always hearing that the earth is in this infinitely delicate balance, and one tipping point goes and then it's going to set off everything and it's going to be one disaster. But are there like other stabilizers, other guardian angels? And is it possible to come up with a bigger kind of model where tipping points are connected to each other and there are these stabilizers? And so we can see with what stabilizer the tippings can all be saved.
I think the various tipping points, having to do with the carbon cycle in some cases, having to do with ice sheets in some cases, having to do with forests in some cases, span across various domains, and so probably have very different physics, and they're interconnected, of course. I think the most recent paper, I think, on this, if I have it here. Yes, this one, right? So monsoons is no longer a tipping point, but there are suggestions of cascading relationships amongst tipping points. I would guess there are very different governing principles behind each of the individual tipping points. Are there sort of cross-cutting ideas that connect the various tipping points? I don't know, but would they themselves contribute to our understanding of the individual tipping points? I suspect not. I suspect each of the tipping points have to be studied in isolation. And there might well be connections between the two. Let's take an example, B and C, right? Arctic sea ice and the Atlantic circulation, for obvious reasons, freshwater forcing in the North Atlantic. C and A, Atlantic circulation and boreal forest, through impacts on the hydrological cycle. So there might be a case for oceanographers to study, I guess, C, and people who study the carbon cycle and the land surface and all of that to study D. And there might be some scope for interaction, but I think we have to understand those elements in of themselves.
So is it true that for B and F, for example, there is no hope at all? It's going into a tipping point. Arctic sea ice and coral reefs.
I don't know. These are beyond my expertise, but I think these are quite vulnerable. These are perhaps among the more vulnerable systems.
I think there's a distinction between tipping point and loss. And maybe the case that we're going to lose Arctic sea ice, and it may be the case that we're going to lose coral reefs just because of the warming. But that's not the definition of a tipping point. It's something that happens suddenly. I mean, this may be just a gradual loss. So you shouldn't confuse the two. So it may be pessimistic, and then I think coral reefs are going to go to some extent. I don't see a way out for that. Arctic sea ice, there may be some hope for that, but we'll survive without it. Polar bears won't, but humans will survive without it. But not all of these mechanisms are in ESMs, but some of them are. So to the extent that the tipping point, like permafrost is not in ESMs, but rainforest is only there to a limited extent, but Arctic sea ice is there. All the processes are there mostly. Atlantic circulation is definitely there in ESMs. And Greenland ice sheet is not being put in ESMs. So to the extent that there are tipping points and they are interconnected, the model you asked for, that is in ESM. To the extent it's represented in ESM. And at the moment, the ESMs don't exhibit tipping points for these subset of what's there. But again, the models aren't perfect. But if I had to choose between simple models versus complex models for the same process, which is in the complex models, I would go with the complex models. But if the process isn't in the complex model, then you have to go with the simple model.
Yes.
Maybe if you put Vladimir Putin in your complex model, you might have a tipping point, no? If Putin is introduced in a complicated Earth system model, you might still get a tipping point.
Which is sorry, but just to take that, but let me ask it, and I know nothing about this, but the experts on dynamical systems also here. I mean, just from a dynamical systems point of view, what is known about tipping points? That is, just to take your model, your example, let me take a system moving in an n-dimensional space, throw down some kind of a potential, and have the separation of timescales. The potential changes much more slowly than the particle moving around. I add some noise to the particle, let's say. Now, generically, I know nothing about this, but I might suspect that for some class of such setups, you will have tipping points, and maybe for another class you won't. And this must have been studied a lot, I would imagine, in dynamical systems, no? So I was just wondering, sorry, just in case. So maybe if that's known, we can, I mean, say something that it has to be complex enough or have enough feedback or something to get rid of.
Or not relevant.
Yes.
All the basin boundaries are tipping points, right?
Yes, that's right. Anything with principal nonlinearity is worth studying, and I think that's been the motivation for studying tipping points, the recognition of individual processes which might give rise to this kind of behavior. But they've all thus far focused on bifurcation-induced tipping, and given the prevalence of, and many of these might be prone more to bifurcation-induced than rate-induced, given the timescales, right? And given the timescales of response. But some of them, like the Atlantic circulation, are definitely prone to, in principle, in the simpler models, rate-induced as well. I think given the importance of the details of the model, I don't think we can map, say, general theories of tipping, just based on understanding spectra of, say, quadratic systems to, climate systems, because then the details really matter. And, we don't have, the kinds of symmetries that give rise to, simple analyses in these very idealized models. We can't directly map those models. There's always differences. You can't take, say, a gyrostat and say it has similarities with, something in climate, but then you have to add forcing, you have to add dissipation, and that might make all the difference. And so it's not very clear. It's not very clear that an abstract approach to this might be as fruitful. I think the strategy has always been to look at very particular systems and then study them for what they're worth. There's lots of work to be done. Yes, yes, absolutely.
Okay, so any further questions? All right, so then we meet at 4 o'clock. We'll have Krishnan resume his talk. Thank you.